arbitrage. There's no arbitrage. So that's the, let's say, the financial idea behind this. Of course, I promise you, if you get all through this, and most money you will later make by finding out arbitrage. So, but for this you have to understand what an arbitrage is, because to figure out which properties of the market tells you that there is an arbitrage somewhere. And so, like in the mathematical world, it's something like this. An arbitrage is if a local martingale is not a true martingale. Then you find arbitrages. And perhaps at the end of the class, you understand this a little bit more. That this martingale property, which enables you, which I try to explain, to replicate. And arbitrage you always have is if you have no replication, but then you have to be lucky. You have just a positive probability to make money. Not in all cases, but the only conceptual way is if you discover arbitrages. But in order to know this, you have to know what an arbitrage is. Mathematically. So we come to this.
Sir, I think your screen is freezed. You please check once.
Which one?
Yeah. Please move your screen. Yeah, now it's fine. It's fine. Yeah. Thank you. Please.
Okay. We come to arbitrage relations. So these were products, and I told you, okay, we have, if you ask for the interest rate, but also like other markets. Here you see the up and down. They have interest rates, currencies, indices, and so on. So from a conceptual point of view, you have no market frictions. This means if you sell and buy, you have the same price. As I said, that's the simplest models. Of course, in mathematical finance, there are also models which take into account this bid-ask spread. But what we try to understand in this lecture is the most regular model, most regular markets, which are, of course, abstractions of real markets. And as I said, we have no default risk. We have rational market participants. Of course, in real life, there are many non-rational market participants. We like all the retail people. They don't finance at the cheapest interest rate. They finance if they have money. From an economical point of view, that's not rational. Even you just finance if the interest rate is the lowest. And next one is what's called competitive markets. This means all transactions are small compared to the entire market. Of course, that's not true. Like I remember when I was working for Deutsche Bank, they always cornered the future. This means they know when people have to deliver something into the future. So before this time, they bought all the bonds. So if people want to deliver bonds, they have to buy it from Deutsche Bank at a high price. The big institutions, and that's not the only one. Every investment bank is just big. They know when people have to buy something in the market, and so they buy it before they can sell it at a high price. But we as mathematicians, we are, of course, honorable people. We assume it's competitive. And absence of arbitrage. And that's a concept we will formulate more mathematically. It means that an investment which don't give you return in future also doesn't cost anything now. You can put it like this. Okay, here you have an example. You see here we have a call price. Just put it into the market, and we will later see that this call price is not proper. If this would be the call price, we can arbitrage, we figure out an arbitrage. So let's assume we have a market where you have before a bond, a call option on an equity, and with the following prices. And we have, again, the market structure, it's going up by 75 and it's going down to 75. Today, everything is, the risk-less rate is 1.25 to 25% interest rate in this case. Huh? Now, so you have investor has 25 euros, and you have we can invest. You buy 10 bonds, 10 shares, and 25 calls. Huh? That's your investment. And then your portfolio at one time t. Yeah, if it's going up, you go through all this specification and so on. Huh? So your bond is 12.50 in both of the cases because we have 25% interest rate. Your share goes up to 10 shares, so it goes up to 75. If it's down, it goes down. And the call has no value if it's going down, it's going up to it. So your portfolio will be in an up scenario will be 48.75, and in the down scenario you just have 20. Meaning in terms of gains and losses, out of 25 you have make loss of 5. Here you have make gain of 23.75. Huh? Okay. And with the same money, you can invest differently. You can also buy 11.8 bonds. That's a market assumption that you can buy parts of bonds. You buy 7 shares and you buy 29 calls. No? If you see this portfolio, you only have to pay 24.6 euro. No? This means it's 40 cents cheaper. Now you go through the cash flows. No? And you see also for this portfolio, for this one, you in the up scenario you have 48.75, and in the down scenario you have 20. Yeah? You have now 2 portfolios which have at maturity at time t the same value in all scenarios, which are only 2 in our case. But portfolio 2 is cheaper. You can just save 40 cents. Yeah, and then you see how you can construct an arbitrage opportunity, an arbitrage strategy out of this. Yeah? The arbitrage opportunity then obviously sell portfolio 1, so you get 25, and buy portfolio 2. Then you sell for 25 and you buy for 24.6, you have 40 cent gain. But the difference, as I said, at time t, the difference is 0. In both scenarios, the portfolio counterbalance. So this is the one of the prices must be wrong. And that's the call price in our setting, because equities is part of the model and so on. Just the price, it's not even there's nothing about probability yet. Just the potential that you might go up and you might go down. Only, of course, in a scenario where you only go down, or where if with probability 1 you are going down, the values will be different. That's not correct. So also if it's only going down, it's also 0. It's in each scenario, it doesn't depend on the probability of the scenario. There can even be 1. So this is kind of just to explain one example of an arbitrage. So this means, of course, arbitrage is because the call price is wrong, which we will see in the next step. Because we look out. Another one is where we can also just by thinking carefully, we can got also by this arbitrage relations, we get a put-call parity. This means we have a share price, we have a call and a put. Everything with strike 100 and maturity t. We look at the I mean, the Americans, they call it hockey sticks because they always play ice hockey, and so these lines look at ice hockey sticks. Huh?
Yeah.
I think your hockey, they are smoother, your hockey sticks, but in ice hockey, you know, ice hockey, what I mean? Yeah? They are really straight, the sticks. Huh? That's why it's called hockey sticks. And they actually mean ice hockey. Huh? Because America thinks it's only America. There's nothing else in America. So these are hockey sticks. Even hockey sticks in different countries are different. Huh? But they are just these straight lines. Huh? So you have the put hockey stick, it's a red one. So you have an increase if value. Here always you have the underlying price at maturity. This means if it's actually 100, no loss, no gain. If equity price is lower than the strike, you make money. And it's different in the minus call. The call itself, yet before the blue line would go up, but we have minus the call. We sell the call. We are the bank, if you like. Then your payout is like this. And you have the share price itself. So this means if you have one put, you have sold one call, and you have bought one share. Yeah, your payout is always the strike at time capital T, if options are executed. Yeah?
Yes.
That's your portfolio payout is always K, just by considering this hockey sticks, the payout. So this means in mathematical formulas, just a property of function, the portfolio shows a portfolio which depends on a share, a put, and minus a call. So your whole, and then we see that P at capital T, from this picture, from this formula, is always K. This means this portfolio gives you the secure, safe, non-risky payout of K at time T. So what should be the value today? You just discount. That's written in this formula. Then the value of the certain payoff at time t equals e to the minus. That's the value before maturity.
Yes.
And so if it's not the case, we can sell a buy according to this arbitrage table. And then let's say if PT is smaller than the discounted value, then you sell you sell at this one, you have positive cash flow at time capital T, you buy one share, you buy one put, you sell one call, you borrow money at this amount. This is positive, because selling the call is so good, but at time capital T of 0, so you have arbitrage opportunity. Arbitrage means something which is 0 later will be non-zero today. If it's plus or minus, doesn't matter because you can go short or long, you can sell or buy. And in the other way around, so this just tells you what I said before. The value, if two portfolios or contracts have the same value, have a future value, they must have the same value in a time before. I don't know, physics, conservation of mass or whatever. Okay, and so this means without considering any probabilities, we now know the call put parity for European options. The price of the equity plus the price of a put minus the price of the call equals the discounted strike. Or you can always write CT as a function of PT. So you only have to calculate CT or PT. The other one will be a formula of this one. Okay, we don't go now to the American options. We come perhaps later to this, but American options, just to tell you the terminology. An American option gives the buyer the right to buy at any time before T, the share price. So in a European option, you have a fixed, like just on end of March 2026, you can buy BioNTech share. The same, but in American way would at any time until time end of March, you can buy a BioNTech share at the price of a strike price was 150. Of course, because you have more options, more choices in American option, the price of an American option should always be higher than the one of the European option, because it includes the right to buy at maturity. And by these arbitrage arguments, you can figure out that actually an American option has the same price than as the European option. So this means for what's called non-dividend stocks, dividend paying, there are some stocks who pay a kind of interest rate, which is called dividend. So in many stocks in real markets, they have dividends. But if the stocks don't have dividends, the American feature doesn't help you. Or put it like this, it's not rational to exercise an American option before maturity. Therefore, one does not execute an American option before time T, just by considering this arbitrage.
Sir, I have one question.
Yeah.
Sir, in the model assumption, it has been considered that there is no transaction cost. So what are the difficulties in considering transaction cost? Because in real market, every time there is some transaction cost available.
Yes.
But in this model, it has been considered no transaction cost.
Yes, I mean, you would say it's either such a big market that the transition costs are not important. You can put it to zero because it's such a small amount. If you consider transaction cost, it becomes all very different, because then it's you see this hedge. It depends how often you hedge and so on. I mean, then you have no closed form solution of everything. You have under some assumptions, you still can get what's called a price interval, which has to do with the transaction cost. Or you have a hedge price, or a buyer and seller price are then also different. But it's all but the basic idea, you can also replicate, but you have to keep track of your, put like this, do you know stochastic analysis? It's then quite a stochastic control problem, because then you are hedging your portfolio. What you hedge is a control, and the cost of the control, you should keep track in a controlling problem. I mean, if you just know controlling theory without stochastic, is the same. So this becomes more involved.
Sir, but then how can we compare with the real data? Because in real market, there is always some transaction cost.
Yes.
So is this model good for real market data?
It can be extended to transaction costs, put it like this. But it has the same features. You still have arbitrage free, but you have not a unique price. You have, again, also for calls and puts, you have a seller and buyer price, and you have to think whether you want to invest on this. But still the same techniques apply with modifications, and of course with different results.
Okay, sir.
So it's like you, in any, like when you do mathematics on a real object, you have different level of abstractions. And this level of abstractions is, in some cases, really applicable, in markets where you trade all the time with very low transaction costs, that's reasonable to do this, to do it like this, or to get a basic idea of the price. Of course, nobody would calculate a price only based on this formula. Usually in investment banks, you start to do this arbitrage-free pricing, and then you think, okay, I need to add this for transaction costs, I have to take this for capital cost, and so on. But the first step is you have to understand the non-arbitrage theory if you want to deviate from the non-arbitrage theory.
Sir, you mentioned that this transaction cost often is taken care by stochastic control way.
Yeah, for example, yeah.
Okay, so would you please suggest some literature? Those who are interested in that dimension, they can explore, or even I can explore any reading material, any research paper, or any book which discusses
yes, but
stochastic control.
this I don't know out of my head, so but I have to see. Huh?
Okay.
I can provide it tomorrow. Yeah.
It's okay, sir. Because some of the participants might be interested. Some of the students might be working in stochastic control, or they wish to work in stochastic control. So if you suggest some readings, it will be beneficial for us.
Yeah.
Yeah. Now you please continue, sir. Yeah.
So I now, so if there are no questions, because I just want to shortly do now really mathematics with where everything is defined. So far it was a kind of more educational simplification without proper definition. Now we want to define this properly. So it's already part of lecture 4, but it's quite a lot lecture 4. So we get now a fully blown mathematical finance with definition of markets, with definition of arbitrage, and so on.
Yeah.
Okay, we have, of course, as in real life, we have more than one asset, namely D asset, D plus 1 asset, S index 0. We have one period, so we don't have time as an index. The index is now the numbering of the assets. So S0 is assumed to be the riskless one. This one is riskless.
Yeah.
And we have
so
D assets.
one riskless and D risky assets.
Yeah.
Okay. Yeah.
And so our, let's say, theoretical setting, our space is finite. Probability space, there's finitely many scenarios, capital N. And the sigma algebra is the set of power, the power set, the set of all subsets, and the probability of each scenario is positive. So this means, and of course, this the probability, then everything is well defined. That's all you have to know about probability theory at this stage. And then we have these random cash flows, prices, securities. Before we had just up and down. Now we have, for n, capital N scenarios, we have values. That's just a vector. For each I, it's a vector in Rn. So the entire, which was before with just up and down, in this one period, is now a vector, or more precise, is actually a matrix. We have n, capital N scenarios in D plus 1 asset. So the entire market, or the future market, what happens in here at time capital T, is described by a matrix.
Yeah.
And then we have this portfolio, which is just how much we invest in riskless assets and in asset number D. Mathematically, we so far have a matrix S with, this is a column, with column S1, which are the state, S0, which are the state of the riskless asset at all the n scenarios, which we assume probably to be just the interest rate, and then S1 is a vector of length n, which gives you the n different value. It might not be different, the n values in the n states. Okay, and this phi I is how you invest. Yeah? They can be, just to make it clear, it just, as is written here, it's just a vector in D+1, how much you invest in your D+1 assets. Huh? So this means we have a matrix. Yeah? We have this here, we have a vector again, the P omega I is a vector. So everything is, you can count if you like. Huh? And then we have the potential investments. Huh? So if we invest according to psi I, now you just can forget, if you like, about the words. You have matrix, you have vector. I don't know what you like, whether you prefer to have it formal or to know, let's say, the meaning of a vector in this case and of the matrix and of the phi.
Yeah, I think matrix would be comfortable, sir. I mean, yeah.
Excuse me?
It will be comfortable for all. They can simply understand that there are n scenarios and then it is a d-dimensional vector.
This one,
Yeah.
So this means my portfolio, which is phi, is a vector, just equivalent to call it portfolio, value today, it's phi I times Si 0, and I sum it up. That's the value of my portfolio today.
Yeah.
And in future, it is matrix multiplied in each scenario omega. Now we are, omega goes from omega 1 to omega n. In each scenario omega, it's just this sum I is equal 0 to d, my investment phi I, times the value of the I asset at time capital T in scenario omega. And so if you now introduce a matrix I was talking about, you have in each scenario a vector. The first column is scenario 1, omega 1, so you have D+1 values of your D+1 assets, and so on. And so you have scenario, the nth column is the scenario n, and scenario. And this is an asset 1 in scenario n.
Yeah. So now,
so mathematically, you are now on safe grounds. You do linear algebra.
Yes. Okay. And from here, it is very clear that whether they want matrix or vector, both are comfortably written.
Yeah. Okay. And then you see, and then you can say we can write the portfolio in the different states as a vector. Your S phi equals this vector. In each of them, and this one is in Rn. These are n numbers. First number is value portfolio in scenario 1, nth numbered, and so on. And what is now an arbitrage opportunity? As I said, so we start with 0. That's our starting value. So you don't have to invest nothing, meaning by selling and buying somehow. Some things you sell, other you buy. It costs you nothing. And arbitrage is if in each scenario you have no loss, it's positive, and you have at least one scenario where you have a gain. This is an arbitrage. Like in up and downs before, it might be that only in up you have a gain, in down you have not a gain, doesn't matter, as long as you have always no loss. Always no loss, and sometimes gain. Never loss. Sometimes gain. And then you can invert it, saying, okay, you have in negative investment and you get positive out of this. So there are different formulation of this. You can reshuffle. That's now an arbitrage. Okay. Now we define markets. A market is a vector B, which are the starting values, called S0 as well, if you like, and a matrix S, if we have done it before. That's now mathematical objects. A trading portfolio is a vector, and a trading strategy this is the same with just we call it H, is called an arbitrage if you have this property starting with negative and getting something, starting with something non-negative, non-positive and getting something out non-negative. And one where you have an actually gain. And that's a reformulation of this. I mean, this. Okay, this is because everything is now in matrix. You can rewrite it geometrically. It's linear algebra. So this means if there exists an arbitrage opportunity, call it phi A, if there's a vector in RD plus 1, then the vector minus S0, my starting value, and the values in all future scenarios, that's a vector in Rn plus 1, starting, no scenario, n scenario, this here are n scenarios. This is in Rn. And my end in the n scenarios I do. And arbitrage just means that this vector of current minus current value of portfolio and all future values is in the set gamma, which is all potential. It's more or less the image of these two, of these matrix, of this vector applied to, you see this is the image of RD plus 1 under these transformations. It's linear algebra. So this means it's reachable. X, all values such as X is an initial value, minus an initial value, Y is the outcome value, all states, and this must be positive in the sense that at least one of the entrants is strictly positive and the other are non-negative. So this means defining the set in terms of the payout matrix and the starting value. Then there must be this must be empty. Again, minus current value of portfolio and all future values gives you a vector in Rn. If you run over all phi's, then there shouldn't be any phi A such that it's in gamma, which are all reachable ones. So there's no A here. All reachable ones. And one, and all reachable cannot be on one entry strictly positive. Just a translation of this condition into geometry. Because why do we do it? Because we know that we have a hyperplane separating or whatever, that we have this fundamental theorem of arbitrage theory. There's no arbitrage if and only if there's a vector psi now in Rn, which is strictly positive in all entries, such that this matrix S applied to psi equals the initial value. And you can check this. I mean, I don't know whether I should go here into the proof. Then do I have a picture here? But that's really separating. So let's assume.
Sir, you may explain in brief if you wish.
Yeah.
Or maybe.
Yes. So let me see. Do I have a picture here?
Yeah.
I don't have a picture here. separating. So separating hyperplane means so we have a set K, which is just a second. So we have a linear space gamma, and I would say a complex, that's your gamma. It's a linear space because gamma are reachable. And you have a convex set K, and they have no intersection. And then we get a vector such that the angel this is my gamma, and I have always a positive. I have something which is rectangular to this one, and with has positive angel with all the other ones. Positive angel, and rectangular to K. Now this I can always find if there are a linear space and a convex space I can separate. Even if I say it's from linear algebra 1, also in Germany it's not taught in algebra 1. So in my lectures I usually prove also the theorem from algebra 1, from linear algebra. But from a picture it's something like this. This is your gamma, linear space. That's your K, a convex space. They don't intersect. So you find a vector which is rectangular to K. And which is positive. So sorry, vice versa. Here it's a rectangular and it's positive angel here.
Yeah. Geometrically, it is more beautiful.
So it's positive. And lambda. It's here positive. Okay, so separation tells you there's some additional space, put it like this, so that we can put a vector here. And from this vector, this vector is rectangular. And of course that they are all we know that they are all positive. Because of this one. We can choose lambda in Rn. And we take set for all set in K. This one is in K, because it's K. We intersect this with this one. So we know that all entries of lambda are positive, are strictly positive. And then we can normalize it, and then we get our Psi. And all the, if you translate now the rectangular property and the positivity property, you get exactly the property that this S psi equals S0. Because we are in Rn plus 1, where we have the initial and the future one. And if this is 0, this means everything can be reached. Everything in S0 can be reached. So this means from this separation, that this is empty, with a convex set and a linear set, a specific linear set is empty. We figure out the existence of the psi. But this means that we have S psi equals S0. It's a kind of, to some extent, your S is invertible.
Yeah.
And so this is also a name. I mean, this is also understood by the economists, with simple linear algebra. So this vector psi is also a name. It's state price vector or deflator. So again, it's positive, and it's only strictly positive entries. And somehow it's in dimension Rn. N is the number of scenario. It gives you a weight to scenario. To each scenario gets a weight Ci. As a probabilist, we can rescale it. Because all these properties are invariant under scaling. We get a probability out of this.
Yeah.
And so this gives us our risk-neutral probabilities. So the economist or some mathematical economists, they just stop here. Okay, that's fine.
Yeah.
I have a weight on each of the states, or a price, kind of a unit price of a state. Let's say if C1 is 1 and C2 is 2, then my scenario 2 has double the weight as C1. And of course, once you have weights, you can reinterpret it in a finite space as probabilities. So this means if there is a market, there is a psi, and we know, and we then this nowadays also economists know it now, that you can really rescale it to get a probability. And this matrix, this matrix properties, S psi equals S0. If you weight the scenarios properly, you got the prices. This is again each 0, 0. This is a vector of length d as 0, 0. This is in Rn. And each scenario, here n scenario, each scenario gets a weight psi. So this means economists would agree on this, it's reasonable, that you have a state price vector, a deflator, in order to have no arbitrage. Because they think in this, let's say, positive or order terms. So then we have, if we have this vector, no, this is which we get from linear algebra. If there's no arbitrage, then we get this vector psi, and then the next step, the normalized psi divided through all. That's the probability, or our P I star, if you like.
Yeah.
So that's the abstract background, which also exists in if you have continuous trading and so on. Then you don't work in linear algebra. You work in like functional analytic arguments, but you get the same state price vector, which is kind of, if you like, a density. You get the risk-neutral density, or in probabilities, you get an equivalent martingale measure, because the space of martingale measures is also a nice properties, as nice properties from a functional analytic point of view. Okay, as I said, so here we construct now we call it Q, is the same as our P star. Q is our P star, which we had before. Yeah? But now not a small p, but really a distribution p. Yeah? And you have a density because we assume it's under the probability measure p. This was the only assumption. All are positive. Yeah? So we can divide, so we get a density. So that's important later if we do like Gesanov transformation or whatever to get our martingale measures, that the pricing measure has the same zero sets as this measure we started with. That's the only, the only place where we use P, the historical measure, however we get it. Yeah, the only technical thing we need is that the pricing measure has the same zero sets, so that we can get the density. This means our Q has the same zero sets as the historical measure. And then to some extent you understand crisis comes if the historical measure is to some extent too much different from our pricing measure. Okay, so this is the main theorem. A market is arbitrage-free if and only if there exists an equivalent martingale measure.
Yeah. Yes.
The martingale measure again comes from this remark. That's a martingale property. Now, in this case, we have just one period. That's a martingale property. On average, discounted, we have the same as today. And if we do multi-period, martingale measure. And these Qs are also called martingale probabilities. And even in old times, if you believe it or not, there is a kind of a betting system, which is called in like horse races or whatever. In any kind of way you bet to some, and so it was actually called a martingale bet, which didn't look at the statistics of martingale betting does not look at the statistics of the horses. It does look on the settings of the other players, which are somehow their prices.
Yes.
Okay, but that's more on the history of these names. Martingale actually came from horse racing. Okay.
Yes.
Again, so this is all I want to talk. The one period. I mean, it's once you have understood the underlying linear algebra, which I was not exact here, but basically what's called the separating hyperplane theorem in linear algebra gives you the equivalence of arbitrage-free and equivalent martingale measure, which I think is a deep insight. It's of course an interpretation of a linear algebra result. But so we will see later that also it holds for more complex models, and so you understand if there's complete markets, non-complete markets, it's all to do with these martingale measures, and which we will see later is more or less equivalent of there is a hedging strategy, which we don't see here. How we get the hedge here, but we can also. We don't do it today, and we perhaps do it tomorrow. Okay, thank you very much.
Yes. Yeah, thank you. So, sir, thank you very much. And we are winding up here the second session by Professor Luc Obeck. And we will